Today we're going to continue our discussion on logistic regression. In the previous video, we introduced the log likelihood function, also called the logit function, and the characteristic S-shaped curve that you see in a logistic regression model. In this video, we are going to discuss how to use the logistic regression model to estimate probabilities or odds, and also how to interpret the p-values to determine if particular coefficients are significant. In this video, we will use the Donner dataset, which is from Chapter 7 of the textbook Practicing Statistics. In 1846, a group of 87 people, called the Donner Party, were headed west from Springfield, Illinois to California. The leaders attempted a new route through the Sierra Nevada and were stranded throughout the winter. The harsh weather conditions and the lack of food resulted in the death of many people within the group. This is a common example of a logistic regression model where the response, survival, is either yes or no. If they survived throughout the winter, we gave them a 1, and if they did not survive, they received a 0. In addition to survival, we know whether they were male or female, we know their age, and we know the number of family members that were traveling with them during this time, called the family size. Just a small note, children 5 and younger were removed from the dataset before the analysis was done. In addition, note that family size can include people with different last names. Using this data, we created a logistic regression model with 2 explanatory variables, gender, where 1 was a female, and again, the age of the people within this data set ranged from 6 to 65. As we showed in our earlier video, the logistic regression model has the following form, where the B0, B1, and B2 are the coefficients for a regression model. B0 is 2.529, B1 is 1.89, and the coefficient for age, B2, is negative 0.108109. So we can use this model to predict the probability of survival. For example, let's assume we want to predict the probability that a 40-year-old male survives. So again, 0 represents male, and for age we put in 40, and we can see the predicted probability of survival is about 0.14, or 14%. In the same way, we could predict the probability of survival for a 40-year-old female. So again, we use the age equal to 40, and for gender we use 1 to represent female, and we see that the probability of survival for a female is 0.52, or 52%. So the logistic regression model allows us to estimate the probability of survival for any age and gender that fits within our regression model. Again, just as in regular regression models, where the response is quantitative, we want to be careful not to extrapolate beyond the range of our data. So any estimates based on these methods beyond the range of 6 and 65 should be considered somewhat unreliable. In addition to predicting the probability of survival, we can use the logistic regression model to calculate odds and the odds ratio. A little algebra allows us to calculate the odds for any particular gender and age. The odds ratio is simply the odds of survival for a female over the odds of survival for a male. Mathematically, the e to the 2.5 can cancel out, as well as any age that you use. If we put in age of 40, age of 35, as long as the age is the same, they will also cancel out. Thus, we are simply left with an odds ratio of e to the 1.89, or simply 6.639. We can interpret this by saying, after adjusting for age, the odds of survival for females is estimated to be about 6.6 times larger than the odds of survival for males. That may seem a little bit surprising, that females were 6.6 times more likely to survive than males. However, we have to be very careful. We cannot say that gender causes a difference in the probability of survival. This is clearly an observational study, not an experiment, so we cannot state causation. The statement about causation is one of the most common mistakes made in regression models. For example, D.K. Grayson stated in his 1990 paper that the differential fate of the members of the Donner Party lends strong support to the argument that females are better able than males to withstand conditions marked by famine and extreme cold. This statement, suggesting that females are better able to withstand harsh conditions than males, may seem reasonable at first, but let's consider just changing these words just slightly. So instead of using females and males, we could also put in 6-year-olds and 30-year-olds because we see that the probability of survival for 6-year-olds is much higher than the probability of survival for 30-year-olds. Hopefully it's obvious that 6-year-olds are not better equipped to withstand harsh conditions than 30-year-olds. Other lurking variables outside what we have in our mathematical model could be explaining these differences. For example, it's very likely that parents sacrificed in order to help their children survive. In the same way, in 1846, it's likely that many of the males did whatever they could to help the females survive. So far, we have used expected probabilities and odd ratios to interpret the logistic regression model. Just as in other regression models, we also want to conduct statistical inference. We use Wald's test to calculate a p-value and draw conclusions about each coefficient in this model. For gender, we see that our estimated coefficient is 1.89 minus our hypothesized coefficient value of 0 divided by the standard error, and we observe a z-statistic of 2.52. In the same way, we can conduct a hypothesis test for beta 2, the coefficient for age. And here we see that both p-values are very small. Note that even though these look very similar to z-tests used in introductory statistics courses, the theory behind this is quite different. The calculations of the coefficients are based on maximum likelihood estimates instead of least squares estimates. We cannot use a t-test, such as the ones typically used when we conduct a regression analysis. The Wald statistic is asymptotically normal, meaning as we get very large sample sizes, these coefficients will follow a normal distribution. However, we tend to need larger sample sizes for logistic regression than we do for standard regression models. Probably the most common error made in regression models is putting too much emphasis on the test statistics and p-values for each coefficient. Just as we discussed with multiple regression models, these p-values are highly dependent on other terms in the model. For example, the model we've been discussing has just two explanatory variables, gender and age. And when only those two explanatory variables are in the model, we see that the p-values are very small. However, using exactly the same data set, I incorporated several more explanatory variables. In addition to gender and age, I included the variable family group size and their interactions. Notice how the p-values change for gender and for age. Often, people create a full logistic regression model, as you see here, and because the p-value is large, they would say that age is not important in the regression model. So, simply using the p-value from the Wald statistic could cause many people to inappropriately assume that age is not important in the model. As you can see here, the coefficients, Wald statistics, the corresponding p-values, and odds ratios all depend on what other terms are in the model. Instead of using Wald's test to determine which variables are significant, it's much better to use the likelihood ratio test. The likelihood ratio test uses the G statistic to determine if any of the coefficients in the model are non-zero. In this example, our p-value is less than 0.001. Thus, we can conclude that either beta 1, beta 2, or both are not equal to 0. In other words, knowing gender and age will provide a better estimate of the probability of survival. This test is limited because it doesn't tell us which explanatory variable is important. However, it does tell us that in our model, at least one of the variables is significant. While we're out of time in this video, the textbook does demonstrate how to use this likelihood ratio test to determine if adding an additional variable to this model would significantly improve it. The goal of this video was to demonstrate how to properly interpret logistic regression models. Any type of regression modeling with multiple explanatory variables can be a very powerful tool. However, it is essential to understand the limitations as well. Hopefully you can see when people do not understand the difference between an experiment and an observational study, or when people do not truly understand how to properly use Wald's test, very incorrect conclusions can be made. Our goal is to encourage the proper use of regression models so that people can get the most accurate information possible from their data.